So we've got some chairs which are going to model a UDL on the bridge, and we're going to try and work out in a bit more detail how the loads are transferred as downward loads on the bridge deck all the way to the abutments. Obviously these cables are in tension, there's kind of, you can twang them like a bowstring, but there's a bit more to it than that because they're not completely vertical, they go to the pier. You've got a vertical component of the tension which resists the downward force of these chairs, and me obviously, but you've also got a horizontal component going this way towards the bridge, so it's putting the bridge deck into compression. If you start out with this deck here, it's got to take not only the force from the blue chair on it, but it's got to take the compression forces from all the other bits of deck that are to the right of it. So actually the compression increases from the edge of the bridge as you go into the pier. Actually, when we're looking at components of force in the cables, you notice they're at different angles, and this affects, even when you have a uniform load, how much tension force is in each cable. Because the cable at the far end of the bridge from me is much more vertically orientated than this one at the other end. And that means that to get the same amount of force, vertical force, to resist the same load, it's going to have a lot more tension in it. And what you see then is for the same force, the farthest cable is going to have a lot more tension than the cable near the pier. So if we want to analyse this bridge, we're going to have to think of some possible load cases to put on it and how to model them. And this may sound like a bit far-fetched, but the self-weight of this bridge isn't actually a lot because we've used lightweight materials. The most critical case is going to be when we add live loads of people standing on the deck or walking along it. And we can model this, we assume an even distribution as a uniformly distributed load all along the bridge deck. But there's a question. Where do we stop the universally distributed load? Do we stop it here? Do we stop it here? Do we imagine there's another person standing here? Do we stop it here? Do we go all the way to the end? And this brings us to the problem of analysing unfavourable and favourable loads. So let me explain what an unfavourable load and a favourable load are. What we've got is a situation sometimes where by adding a load to a structure, you're actually making it more stable. And when we want to design a structure, we want to find the critical load case. The load case which is reasonable, but is the most likely to cause failure. So for this I will need a prop. Let me introduce Mr. Favourable Load. And he's going to stand on one end of the bridge. And actually, even though he's adding weight to the structure as a whole, he's supporting me by preventing the overturning of the bridge. And if we were designing this bridge and we added a UDL along the whole length of the bridge, it would work very much like this. The UDL on this side of the bridge would actually help the bridge remain stable. So we wouldn't want to include that. It's very important when you're designing something, you think about these things and manage to find the critical case that's going to be the most likely to cause failure.